we're ready. So a very good afternoon to all of you, and welcome to this fifth webinar, this one dedicated to reliability prediction, a comparison study of MIL-217, Telcordia, and FIDES standard. A couple of slides on just advertising the product we represent. The software we used was the LandPredict software, part of a family of product from Soft. And 2 words about ourselves. Tecram is the only independent reseller of Soft product and services here in Italy. And what we do is sales and technical support, reliability engineering training on Soft applications. And we provide official Soft training courses. We also provide light versions, which are sort of workshop, 2 sessions of 3 hours each, and wherever is necessary, custom-made training. And in addition to that, we provide consultancy and coaching. And how you can find us, the website is www.reliability.it. We got a YouTube channel where we are posting videos of the software and also the webinar. And we've got a LinkedIn page where you can find sort of posting link to articles that we publish on our website. And obviously you can contact via the website info@reliability.it. Where you can find this recording, give us more or less a week, because we are migrating to a new web, a new layout, say, and it will be a page on resources, and which will include the video, which are published on the on YouTube site, and the webinar itself. Okay, having said that, we now can talk about this webinar. So in this webinar, we're going to present a desktop reliability prediction of a BOM, bill of material. We've analyzed it with 3 different standards. So as we say, we analyzed it via LandPredict using the configuration of MIL-217, notice 2, the Telcordia SR-332, issue 3, and the FIDES 2011. So first of all, what is reliability prediction? Reliability prediction is a desktop analysis performed on a system, starting from what it is the whole list of components. And in order to establish the reliability of this layout, and it takes into account the intrinsic characteristics of the components to derive the failure rate. And for intrinsic characteristics, we mean things like technology, the type of packaging, the manufacturing quality, what are the environmental factors, etc. So essentially, a failure rate is an index that, essentially, the failure rate is an index that will tell us how good or how bad the component is, and is measured in failure per hours. Obviously, the higher is the number of failure per hour, the worse is the component. And what are the hypotheses? The component has a constant failure rate, i.e. this failure rate does not change in time. So what we'll do a round on the 3 standards, just to have an idea. Before then, we show what we obtained from the analysis of these 3 standards. So the first standard is MIL-217, the first prediction standard of its kind developed by the US military, and it is an empirical method. Okay, and it's got 2 methods of analysis. It's got part count and a part stress. It was developed a long time ago, and obviously today is largely outdated. And if possible, a new model or a new modern prediction standard should be used to obtain more accurate results. And we will see that what we mean by accurate, because what we've done, we've put together, we've analyzed not so much the entire BOM, which we did, but also we wanted to analyze different components and with a different standard, and measure them against the manufacturer results, so that we would have some idea how far we were from the manufacturer prediction. So by going back to MIL-217, part count analysis is a very simple one. It's basically a sum of a failure rate reference, if we want, which is an average, is a typical typical operating condition. So typical environment, stress is very sort of mild environment with reduced stresses on a component. And this, doing the sum of this component, obviously we assume a sort of zero system, doing the sum of this component, we will obtain a figure that represents how bad our bill of material is. And this was, if we look at how, or when it was created, the objective of this methodology was to compare two different solutions. What happens if I use this type of components? What happens if I use this other type of components? And measure one against the other. And then obviously choose the one that was more appropriate. And once we choose the one that was more appropriate, we were going into a detailed design. And by doing that, we will be able to characterize better our design in terms of stresses, in terms of environment, in terms of temperature and things like that. And we were able to get a better idea of what was the actual failure rate of our configuration, rather than a sort of a generic type layout. So the base failure rate was derived from linear regression applied to field data. And we looked at some of these data in one of the reference we will see when we talk about the diodes. Okay, and the resulting equation depends on two main factors, the temperature and the voltage stress. Voltage stress intended as the ratio between the applied and the rated voltage. In addition to that, we got other factors that come into the equation, quality factors, environmental factors that are attached to the equation as appropriate. And those will change according to the components we are considering. So here we got a simple example of a capacitor. And we got the part failure rate is the base failure rate multiplied by this factor. We got a pi CV, which is a capacitor factor, a pi Q, which is a quality factor, and a pi E, which is the environment factor. And this is very simple, obviously, interpretation of that into the program to obtain what it is, a failure per million hours. Here we're on these standards, we're working on a failure per million hours. And the prediction factor, and I don't want to get too much into formula, but we are presenting the three different standards, and there will be, for sort of half of the presentation, a bit of this, unfortunately. Then we'll obviously go into a more practical approach. So, and here we got the base failure rate, which takes into account of the voltage stress on a component and the temperature stress on a component. As we can see, as a parametric, it's a it's a practical interpretation, obviously including the temperature model of how the component failure rate varies with the increase of temperature. But in fact, we can see there are some various parameters that sort of adjust, it's an empirical approach, parameters sort of adjust the results. And what it does, it uses a lot of these tables that reflects, obviously, a military environment from ground Benin to cannon launch with what is considered to be the multiplying factor to our base failure rate. That's for pi environmental, and there's a pi quality, and so on. So that's the approach, and we'll see how, for example, a FIDES approach is quite different, although it is the same. It is the same application, if we want, because again, it's aimed at the military field predominantly, but it also applied to other fields as well. But we'll see that the staggering differences between these two standards. So what are the limitations of MIL-217? Diverse environmental factors such as humidity, vibration, pollution, and things like that are basically modeled with a number, essentially. Similarly, quality, again, is the same. Disregarding differences in material or architecture, again, that's just a number. And so in a sense, so we take a very simplistic approach, and but we don't want to condemn what they did, because obviously they did a very good job when once start looking at what's behind the actual MIL-217. But it is a very different approach from, as I say, standards like FIDES. The other aspect is excessive focus on component level failure rather than system-wide failure. And we looked into a study which we are not quite sure whether it came from PRISM or somewhere else. That's why we put the sort of double question mark on that. But certainly it points at 78% of failure may actually cause outside the component itself, and is to do with the environmental factor, for example, extreme temperature, inadequate cooling, so problem with design, error in manufacturing or assembly, material defects. So there are all aspects that obviously ultimately condemn the components to a failure, but they're not, but they are possibly they could have somehow avoided by a better design or a better process in place. And the results are therefore considered sort of rough estimate. They're heavily reliant on a specific manufacturing characteristic of the component, which has become, not may become, has become obsolete. Okay, and another limitation assumes that the failure rate is constant over time, disregarding physics of failure and failure mechanism. And also ultimately ended up being not recommended. So if we look at these references, basically, and that was at the end of the century, turn of the 21st century, essentially it was declared for military application not to be used because of its unreliability and potential misleading prediction. And I think that had to do, if I remember correctly, with the F-15 warplane that the war procured in the United States, where the results based on MIL-217 really gave a very bad projection. So we move on to Telcordia, and Telcordia was created from the ashes of MIL-217. It was created by Belcore Laboratory, and in fact is heavily based on MIL-217, but adapted specifically to the needs of the telecommunication sector. In fact, in a sense, in the telecommunication sector was quite active in those years because there were standards from British Telecommunication, there were standards, I think, from France Telecom, standard from Italtel here in Italy. There were standards all over the place relating to the telecom world. And reliability prediction can be further refined by combining with results from the lab or from the field. So unlike MIL-217 that gives you a number and you live with that, with Telcordia SR-332, you can integrate laboratory test results and field data, obviously, if you have them. And how does he classify the equipment? He calls devices the actual components, and then and this is where we worked essentially. Then he provides a result for LRU if we just sort of combine components. And then it's multiple LRU potentially can develop into a serial system. What it does not include in terms of failure, because there's quite a vetting process to, once the data is collected, to establish whether the failure is acceptable and has to go into a database or not. Transient failure are not included. Manufacture error, process induced error are not included. Software failures, and anything to do with sort of systematic failure, essentially. So those are not obviously included. And what we used the steady state model, or the steady state approach, if we want, which will produce a base failure rate, and it produces also a standard deviation of the data. So it produces a variability of the data, although we don't actually see the standard deviation, but we see the confidence interval of our projection. And it puts together, and also includes the pi quality, pi stress, and the pi thermal. And this is called the black box approach. So it's a method 1 on a device, or 1D on a device, and it's called black box. Then there is a method 2 on a device, black box plus integration of laboratory data. And from lab data, then we can integrate if you have previous burn-in or if you didn't have previous burn-in. And then we got the method 3 on a device. It's again a black box with the integration of field data. And if we have burn-in, which we didn't have obviously, we can also have a pi early life that will give us some information about the initial part of the failure rate of the component. So this is what we obtain. Basically, we got a base failure rate with the various pi and the standard deviation with the various pi. And when we integrate at unit level, in our case at a block, then we add on also the pi environmental. So environmental is not integrated at component level, but is integrated at the block. Okay, and then the sum of these can basically make up the total system. So if we got plenty of blocks. So what the difference between these MIL and Telcordia? MIL uses an exponential distribution. Telcordia uses a gamma distribution with a standard deviation on all failure rates. And that produces confidence bounds, which enables us to improve the projection if we think perhaps we've been too optimistic. So we want to make life a little bit harder, say. Environmental factor is associated with each component. Environmental factor, in fact, say we've seen, is associated with the LRU. And steady state failure rate represents the result prior to wear, typically 20 years. And again, we don't take wear out life, okay? So, and the reference condition are 40 Celsius, electrical stress of 50%, quality level 2, which translates to a ground benign, and basically all pi's are 1. So we want to use a configuration that would not interfere too much on the actual result. And of course, we had to be consistent, so we had to be careful to make sure that we were using the same configuration. And that wasn't easy because we'll see what happens. Pi stress factor, so we essentially got the pi stress and the temperature stress, and here we got different curves according to the different M value that depends on the type of technology, the type of product, and things like that. And our reference condition is basically a 50% stress level. And in terms of the temperature factor, we have the Arrhenius equation and the reference condition 313, and is the usual activation energy and the Boltzmann constant. Okay. And the difference is, being designed for the telecommunication rather than the military industry, it lacks extreme operating condition, and also it lacks those kind of environment, very harsh environment that we would encounter in a military application. So it's obviously a more gentle application and set of conditions, because obviously it reflects a completely different scenarios. And the technique assume a failure rate follows a gamma distribution with shape parameter K and a scale parameter phi, and the procedure is used to obtain a more accurate estimate. Say we can go from 60% to say 90% if we wish, if we want to obtain a better results. Okay, and that takes us to FIDES. FIDES prediction standard is a French standard, and at that time, the French market, in a sense, has been very, very active in developing very interesting standard. I remember in Lander Predict, one of the very early versions, there was another French standard that was called RDF 2000, and that standard was for the telecom sector, if I remember correctly. And it became then an ITU standard, and now it has developed into an IEC standard, 62380 or something like that. But basically, we'll see they both got in common a very thorough assessment of by a physics of failure and by a mission profile of what is going to be the reliability, rather than just using multiplicative factors, which are these pi's. So the objective was to make a realistic evaluation of the reliability of the electronic products, and for FIDES was jointly developed by the basically the defense and aerospace world of France. So we're talking about Airbus, we're talking about different division of Thales, we're talking about Eurocopter, MBDA, Nexter. Some of you will recognize this name. And to provide a framework for reliability prediction, which is more refined than MIL-217F. Given that I've got this list of names, I just mentioned the names behind the Telcordia. The names behind Telcordia are Alcatel-Lucent, Nokia, Ericsson, Cisco. So obviously it's a completely different world from the military world that we see here. Okay, and it's not just military, because in fact, in that standard, basically say the standard could be applied, apart from military, to railway application, to telecommunication, to the space industry, to the Navy, to the aeronautics, to the automotive, even to the household appliance. In fact, there is a mission profile of a washing machine, for example, in a standard. So FIDES is a prediction methodology based on physics of failure. So that makes it quite different from an empirical method that we've seen in MIL-217. Supported by analysis of test data, feedback from the operation, and existing models. So there's a lot of, obviously, it's like a closed circle where you collect the data and review, internal peer review and things like that, and then you decide how you're going to integrate the new data or discharge it. That, in a sense, is similar to also the Telcordia. Calibration of the final model via expertise of consortium member, particularly for process factor. And the sort of difficulty that emerge is obviously reliability is something that changes in time. We got the poor knowledge of the real life of the product. That's obviously when you got product in the field, you don't know how it's going to be used. You don't know the stresses that it was subject to. The separation between the product-related failure and non-product-related failure. You could also have batch effect. A batch effect is something that we encountered on a project back in the 90s on a diode for a power circuit of a train, where after 18 months, something like, less than 2 years, something like 3/4 of the fleet had a short circuit diode, and that it was either a bad design or it was a batch problem. And mission profile, you don't know how it's going to be used. There's something on mission profile on the RGA software or ReliaSoft, but that is for reliability growth and how you compare that with what you applied on the field, from the sort of theoretical and what you're applying on the field. Obviously, mission profile, once it's out in the field, you're not completely sure on that. It models electrical, electronic, and electromagnetic components, and it takes into account the technological and physical factor which affects the reliability. But more importantly, it takes into account the life profile. And we'll see what we mean by that. Failure rates predicted by FIDES are hourly failure rates expressed in terms of calendars hours and based on a mission profile. So the results, in fact, that need to be taken a little bit with a pinch of salt, because they say these are results for 1 year of a mission, 1 year of operation. Takes into account thermal, mechanical, electrical overstresses, takes into account failure due to development, production, operation, and maintenance, and those aspects are covered by questionnaires. And in a sense, it's a kind of an ISO 9000 type of methodology, because it's quite rigorous on requesting the information, detailed information on how the product is developed, how the product is handled in the field, and so on. Similar to all the others, failure rates varies according to the bathtub curve, but we are only looking at the constant failure rate. So the infant mortality wear-out stages are considered out of the scope. And what data handles? Data on environment and product usage conditions. So we're looking at operating temperature, amplitude and frequency of the temperature cycle, vibration amplitude, relative humidity, pollution level, and so on. Data on product definition, so that data comes from the manufacturer data sheet. Data on product life cycle, so data on product specification, design, integration, and these are achieved, as well as data on supply achieved by questionnaires. So the fundamental equation of the FIDES model is basically our lambda is a lambda physical multiplied by 2 pi. And this seems simple. If it weren't that behind these 3 elements, there's quite a lot. There's a world, as we discovered. So the pi physical is basically the physical contribution. The pi, can't remember now the name, but will come on another slide. Pi PM, quality control of the manufacturing, part manufacturing, or something like that, of the item. And the pi process, the quality control of the development, manufacture, and usage of the product containing the item. And then we got acceleration factor that basically will change this projection. And here we go, an example of a life profile. So this is originally we set out with 3 phases. Then we realized the impact of 3 phases, so we scaled back to 1. So we have the results that need to be presented in calendar hours up to 8,700, so 1 year. And then we have the mode of operation. And then we have a temperature humidity part of it. So the ambient temperature and the relative humidity. And then we have the temperature cycling. So the jump in temperature, the number of cycles per year, how long they last. And then we got the maximum temperature during the cycling. And then we got the random vibration, and then a pollution level, which is a scale of low, medium, high, or something like that. And then we got the environmental, again, that's another scale, application, and then protection, hermetic or not hermetic. And then this number results from questionnaires, essentially. And this is the one phase that obviously we'll see all these elements will influence, because we're not taking the number, but we're taking the formulas that will handle, we're taking the models that will handle these numbers, okay? And we can see the application of something like that, for example, for a jet plane, say, for example, or for a tank, or for an aeroplane, obviously, where we got different phases, we got different with different stresses applicable to, and we got different length of these phases. So it becomes quite important to detail this information. Probably this information are quite available within the manufacturer. So the model failure mechanism, as far as temperature is concerned, is the Arrhenius model. Okay, and we consider reference temperature of 20 Celsius and electrical stress divided as a function of the technology. So as far as the temperature is the Arrhenius. As far as the temperature cycling, FIDES uses the Norris-Lanzenberg model to evaluate the failure mechanism to acceleration on fatigue, and because of the temperature variation. And this is, for example, solder joint fatigue. And so we got the acceleration factor is the proportional number of cycle. Cycle duration is a power law model. The delta T is also a parallel model, and the actual temperature, the change in temperature, is the Arrhenius equation, the exponential model. And then we got the relative humidity model, which is a parallel model and an exponential model. And then we have the vibration model, which is a parallel model. Okay, so these are the elements that we basically will handle the data that we entered into the emission profile. And then as far as the other element regarding the chemical stresses, so saline pollution level, environmental pollution, etc., those are basically pull-down menu that where you just select you select a voice that is appropriate, and obviously behind the voice there will be a numerical number. So let's have a look now at a practical case study. Right. In the following slide, we present a prediction study performed over a regulation and control circuit. Okay, and about 250 components, and we're looking at capacitor, resistors. So we're looking at passive components, and we're looking at active components. Okay. And what we wanted to do, we wanted to use not a list of components that didn't make any sense to them, but we wanted to use a bomb, if we could find one. And we did search and find one bomb that we could use. Okay. And we also obviously had to be consistent in our approach. And because obviously if we're measuring one standard against the other, we've got to make sure that we maintain a consistency as much as we can, because obviously it's not that easy in terms of classifying or completing the information into each standard. To maintain a consistent approach, all the stresses, all the voltage, power stresses are equal at 50%, and the ambient temperature of the components are 25. And then as far as MIL-217, we raised the quality to military standard, because we had to get, say, the best of what we could get in MIL-217 to compare it to the quality level of more modern standard. All equipment were considered to be, in terms of the environment, a non particularly demanding environment. full model case method as we use a full model as a temperature mode. Components were assumed to be mature, and we used the best setting we could use in the standard. We were dealing with CMOS technology, surface mount, and here we hit a little bit of a problem, because it's asking us the number of transistors that we have to enter in integrated circuits, and of course you don't find that information on a data sheet. And what we could derive, say, okay, 4 transistors make up a NAND gate, but that's about it. And we can't go much further than that, and that's not going to help us in any way, shape, or form. So we did a little bit of ChatGPT on this to try and read the complexity, the package type, the complexity of the actual package, and we sought some advice from ChatGPT to have some ideas. Okay, obviously it gave us a range, and here we've used some of them. We used 1,000, some of them we used 2,000. We may be totally wrong, we don't know, but we did our best shot on that. And those that appear more complex, we assign 2,000 transistors. Those that appear slightly less complex, we assign, say, 1,000 transistors. Having said that, the difference was not stratospheric. It's not that we sort of radically changed the results as a result of changing the number of transistors, but we're trying to be thorough and trying to get as close as possible. On the Telcordia side, we use the quality of 1 and non-interfering quality. We use the same criteria in terms of number of transistors, because the Telcordia has also asked us for a number of transistors. It's a 90% confidence bar, but in reality, this number does not vary, because for the method 1 we used, it was actually 60%, and we use the method 1, the sort of black box analysis, which is the base failure rate with the 3 stresses, with the 3 pi's, essentially. For FIDES, we obviously had to set the mission profile that we've seen. So we set it on, as I say, originally, because the equipment is used as a power supply or power control unit for laptop servers and things like that. Originally, we decided that we were going to put in a typical use of in an office environment, say perhaps more of a laptop rather than a server. And with the idea, we would do a working day, we would do the weekend, and we would do the holiday period. And the problem is then it became very, very long, not very complex, but it became very long then to remap all the components for the 3 stresses. So in the end, because we had originally started with one mission profile, and then we decided to switch to 3 phases. So in the end, we'll scale back to a single phase, and we assume a delta T of 10, 6 hours operation, perhaps could have done more, but we tried other options. The changes were not, as again, obviously they were influencing the result, but they were not completely altering the conclusion that we could draw. 35 maximum temperature, so a delta C from 25 of 10, 0.5 GRMS, which is probably quite high for a computer. We did some tests of the 0.1, but by now all the numbers have been already projected for 0.5, so we couldn't go back and change it to 0.1. And pollution level, all these we put in very low value, low saline, moderate application, non-hermetic protection, and the questionnaires we try to answer. Again, those are not very easy unless you are deeply engrossed in a project, and obviously you got designers and you got a lot more information, who are the suppliers and things like that. So we obviously did our best based on the most reasonable criteria. Now, problems, plenty of them. Problems encountered during the mapping of the component. Difficulty in mapping datasheet data to parameters of the standard. A lot of these problems emerged from the fact that we were doing a desktop study, and that's one of the, we haven't written quite the conclusion, but obviously one of the conclusions we could draw, you cannot do this work unless you're sitting next to a designer. Unless you're sitting next to a designer, someone who can just tell you exactly what are the output parameter, what is the output voltage, what is the power dissipation, and things like that. So on a desktop study, we didn't want to invent things because we just don't work like that. So we had to do the best, we used the best judgment to derive the most appropriate numbers for that. But it was quite difficult, and because when you're looking for a parameter and you don't find it, you go and search how you can derive that. It'll give you a little bit of the answer, but it gives you a new unknown parameter. So you go and find the second parameter. How can you get this second parameter? And the list goes on. So it's basically, it's like it's like a Russian doll, continuously open, and you find a new doll inside, and you don't get the answer of it. So, and different standards ask you different questions. So, for example, the number of transistors. FIDES didn't ask us for anything like that. But FIDES gives us a little bit of a problem on one type of package where he imposed a number of pins. And of course, we didn't have the number of pins that he wanted. So we had to choose a number of pins of our integrated circuit that was not exactly what was requested. But the most difficult one, as far as the integrated circuit, and also other components as well, was the power dissipation. You know, you don't have the actual layout. You don't have a designer there that you can just ask all kinds of questions. And the power dissipation is the static power dissipation and the dynamic power dissipation. Internal equivalent capacitance, you have no idea because you've got capacitance between the drain and the gate of the MOSFET, and every part of the MOSFET there is a capacitance, and you need to know the switching frequency and to know all kinds of things, and basically there's no way you can figure it out. And that's, unfortunately, is a critical parameter. So we'll show you how we've approached to try and get around to the power dissipation. Don't know the load. When we go a circuit, we don't know what is connected. We don't know the values of these things. Component categories. Component category. In one case, we have to switch slightly the category. Obviously, we didn't switch from resistor to capacitor, but we had to switch a different type of capacitor because it was giving us some problems. Number of transistors, we already mentioned that. We didn't know where to start. All things could be resolved. It just needed more time. So we start with resistors, and we looked into data from the resistors, and this is kind of data from FMIDA or FMICA, if we want. Okay, so for the resistor, it was telling us 50% of a failure were due to open circuit, 45% were due to drift, and 5% were due to short circuit. And these are the documents, mainly military document, quite old, but mainly military document, well, MIL book and Reliability Analysis Center book. And we made note of this because when we map every component in a BOM to the actual data sheet. So we open all the data sheet of every component to read the actual numbers. And we were trying to find, the objective was trying to find a component that would publish the manufacturer's projection on the reliability. Because then, as I say, we could measure our calculation with the three standards against the manufacturer calculation. Okay. And we picked up this V-shy resistors, and there was a note that basically said the resistors do not fail if you designed it properly. So, however, you might have a drift as a failure mode, which can lead to, in time, will lead to failure. So, in other words, forget about the open circuit, forget about a short circuit, is 100% drift, essentially. And so we were a bit curious, so we did a bit of search to find out what had changed from old resistors, which projected those three failure modes. And okay, this was only a sample of one, in a sense, so it may not be representative, but we did a bit of research and we found that anti-surge chip resistors had contributed to the change of the failure mode. So we were expecting, obviously changes in technology, and those changes in technology reflecting also changes in results. So we took these resistors and we had the manufacturer data, and that was the observed data. It was the only time when the manufacturer presented actual results. Okay, so the manufacturer gives us a fit less than 0.1, and we obviously converted all the MIL number in fit to be able to just compare them one against the other. We got 155 1.55 FIT, 0.13 for the Telcordia, and 0.014 for the FIDES. And we got this diagram, which I can't see because I got the menu from, so just do a little zoom. Okay, we got a menu from Zoom that is interfering. But we can see the difference between, if we take the reference is the manufacturer, we take in 0.1, because obviously less than 0.1, it could be anything. So we take in 0.1, and that is the decrease or increase compared to our reference value. Again, I don't want to draw conclusion. This is a generic results for all resistor. This is a resistor for this specific one where we could get the results. And then we looked at the inductors. The inductors, and unfortunately, MIL start asking very uncomfortable questions, is asked for the power losses. The power losses, and we figure out is the power in the core, plus the power in the DC resistance, and the power in the AC resistance. And also he wants to know the radiating area in square inches. And he wants to know the temperature rise, which again is down to the dissipation of the power. So we had no idea where to start with this information, because we don't have any information about the design. So we went on to the manufacturer website and we ran a simulation. So we put in what we deem, based on the data sheet and based on the layout of the other components we had, what we, particularly the integrated circuit, what we deemed was an acceptable results, and we got this information: 321 milliwatts, 0.026 square inches, and a temperature rise of 8, which goes from 25 to 33. So we had this information, we plugged it in, and we got the data from the manufacturer for that particular inductor, and these are the results. So we got 0.48 from the manufacturer. FIDES resulted very close with that configuration. Telcordia was lower, 0.19, about less than half. And then MIL was much lower, and so in a sense, we're quite surprised on that. And these are, again, our projection. And if I can find the lens, I can do a zoom. Okay, so they're all below what was the manufacturer indication. Okay, we didn't want to spend more time trying to investigate as to why they were like that. So we just accepted it, and we moved on. We moved on to the capacitor, and that's where we had a lot of problems. So capacitors, we had, they are normally characterized according to two standards. We got a Japanese standard, JISC 5003, which is a 1974 standard, and a more modern one, a JEDEC JST 85, method of calculation of failure rates of unit of FIT. And we went looking for manufacturer data, because obviously we needed a candidate to analyze it and measure it against the manufacturer. And a lot of them published this information, which at the beginning we struggled a bit to interpret it. So reliability 1%, or reliability 0.5%, per 1,000 hours at 85 with 0.1 on volt series impedance, 60% confidence level. And it boils down, this is not reliability, this is a failure rate, okay? But we don't have information in terms of, so these are sort of results, practical results, but we don't have information about the, as these are capacitor, we need to have information about the voltage side of it and the sample size. No, sample size, sorry, is, no, we got a test time, but we don't have a sample size. So this is the model. It's called the Prokopowicz-Vasquez model, and essentially is a power law on the on a voltage and an exponential on a temperature. And for the capacitor, N tends to be around 3, although we've seen some cases also 2. And the accelerator, the activation energy instead varies quite a bit, from 0.9 to 2. So we sort of reproduce a calculation for semiconductors and not for capacitor, just to have a better grip of the method. Okay, so it's a it's only a single stress, so we don't have the voltage and we use therefore a temperature model. And he calculates the upper confidence bound, particularly if you go zero failure. Okay, like here we got a number of hours of test, 1,231 units under test at zero failure, and uses the chi-square method to estimate the failure rate, okay, at a specific confidence level. So we can set the confidence level, okay, and from an acceleration of say 125 and 55. So, okay, we were happy. We were able to reproduce the actual number that they were quoting. So we had sort of the methodology. So we were looking for volunteer to insert in our, we got plenty of capacitor. They were all multi-layer capacitor, except a couple of, with the exception of 2 tantalum capacitor. So, but they were all, otherwise they were all ceramic type capacitors. And we didn't have much joy with one of the components that we had. So this was a TDK capacitor. We didn't have much joy with this component because when we put in the standard methodology that they recommend or that they use, essentially, we had uncertainty on the voltage acceleration. Okay. We also had uncertainty on which value of activation energy they were using, because when you go a range so vast, obviously, the results change significantly. They tend to use this approach. They tend to use this using the temperature in Celsius divided by this phi, instead of using the temperature in Kelvin and using the ratio between the activation energy and the Boltzmann constant. But otherwise, the method is the same. So we went off our bomb and we found another multi-layer chip capacitor, which, of course, we had to do the calculation separately. We had to do the calculation separately because it was not going into our bomb because it was completely, it was another component, okay? But this one, it was an X7R capacitor, which has got a plus or minus range on a capacitance of 15%. It's got quite a large temperature application, minus 55 plus 125. It's a 1H, which translates to a 50 volts in the data sheet. But it's got this number, which the other one, our component, didn't have. It's a 3, which is tested at 1.5 times the rated voltage. So we took the number, sort of 77 unit tested for 1,000 hours at 125 and brought back at 85. We plugged it into our calculation sheet, and we got a failure rate of 27.57 FIT. So we got a 27.57 derived from the calculation, and then we measured it against the recording from the MIL, the Telcordia, and the FIDES. And to our surprise, the MIL was spot on, 25 and against 27. Telcordia was much lower, and the FIDES was slightly higher. Okay. Again, this was just for our own interest, just because we really couldn't go anywhere. We wanted a capacitor, given there were plenty of capacitor. We wanted to be able to present a result for the capacitor, and but this was not inside the bomb. Okay. And then we had integrated circuits. We will just look at 3 of them. And this was the recommended layout, typical layout, say, of this integrated circuit. And again, one of the big problems was power dissipation. So we went round in circle trying to find a way of deriving a power dissipation, not having a design, not having a real design, which is not very easy. So we looked at what was the typical layout, typical values from the data sheet and from the diagram, and essentially we tackled it as power in, power out, and what doesn't come out goes up in heat. Okay, so that's our power dissipated, and fortunately we were guided by an article to look for the efficiency diagram on the data sheet, and the efficiency diagram gives us information in terms of, for different input voltage, which we got here, obviously, and for output voltage and output current. So we had 3 out of 4 because we just needed the input current, and we put our we read out sort of 90% to whatever value we chose, and so we had all the information with just one unknown, and that enabled us to calculate the power losses. So we had our 80 milliwatts power losses, and we could plug it in into our chip and get the results. So we were getting the results, and we had the manufacturer data, because this was a Texas Instrument, and they are particularly good at projecting a lot of their results. So we were lucky in that sense to have manufacturer data. So we had our results, we had a FIDES, so the manufacturer gave us a 0.9. We got 4.35 with the FIDES, 3.4 with the Telcordia, and 76 with the MIL. Okay, so this was the first integrated circuit, and here we can see the actual, and here we can see the actual differences. So obviously the 0 is the manufacturer data. So then we moved on to the next one. Next one, similar arrangement, and we go and read on the efficiency chart what to take, do the calculation, and we get our power losses. We get our power losses, plug it in, get the manufacturer data, and we see the results. So we got 42.8 for FIDES, 3.4 for Telcordia, and 373 for MIL. So MIL, as you can see, is well out of what is considered to be a sort of reasonable tolerances. And then we went on a third one. A third one, we took a different approach. We used the tool that the manufacturer has on their website, and we ran a simulation. So we put in what we consider to be based on the diagram and based on the values of the previous components we used, and we got a power dissipation of 0.514. Again, plugged it in. Again, we had the manufacturer data, and we measured one against the other, and we can see MIL out, completely out, 0.1 against 3.47, and FIDES about 50. So from here, I can just stop a second on this slide. From here, we can see that we didn't have to suffer too much on inputting the data from Telcordia, okay, compared to the number of information we had to go and request for MIL, and FIDES. In some cases were particularly difficult. Obviously, we had questionnaires that once you compile, then you can use, or you're going to have to reassign different questionnaires. But the Telcordia just surprised us how, with very little data, was able to get very close results against the manufacturer projection. And then, I don't know what possessed us, we decided to tackle a diode. Okay, a diode, it was a transient suppression diode. This is a type of diode. And we found it was difficult to configure with our diagram, okay? And difficult to configure the forward voltage, which is relevant for the power dissipation. We needed that. And to cut a long story short, we ended up reclassifying the diode because we could not live with the number if we classified as a transient suppression diode. And I'll just go forward a second. So the diode was reclassified. We didn't have any manufacturer data, so in that sense, we cannot measure against one against the other. But what we found when it was classified as a transient suppression diode, it gave us something like almost a quarter of the contribution to the failure rate came from this little diode. Okay, so but in particular, it prevented us from putting in the parameter. Okay, it prevented us from putting in the parameter, which was the rated voltage and the apply voltage. So we had to change to a Schottky diode to be able to enter these values, okay, to maintain consistency with the others, essentially, okay. But so we looked into, because we spent a couple of days suffering with this diode before we could find a way of getting out of the restrictions. And so these are the formula that we've seen before. So we got the part manufacturing, we got the pi physical and the pi process. And the pi physical is actually is actually the polynomial of lambda and pi's, essentially, because we got a lambda 0 thermal times the pi thermal plus the lambda 0 cycling case multiplied by the pi cycling case, temperature cycling case, and the solder joint, and the humidity, and the mechanical vibration, and then is multiplied by a pi induced, which in itself is another 3 pi's when you start splitting this up. And that is for a single phase. So then if you've got 3 phases, obviously you need quite a large piece of paper to write all this. So these values we selected for our diode SNBJ because trying to understand why things were just so wrong. And these are the base value that we present here. And then we've got, so these are the base starting point if we want. And then we got the pi thermal, which is a temperature model. So it's an Arrhenius model. And then we got the pi cycling case, and that is the power law model on delta T and a temperature model. And then we got the pi cycling solder joint, and that's 3 stresses. Is the power law on a cycle, on a length of the cycle, the power law on a delta T, and an exponential or Arrhenius on a temperature model. And then we got the pi relative humidity, and that is another power law and a temperature model. And lastly, we got the mechanical one, which is just a power law model. Okay, so as you can see, it's quite a complex, and that's just a pi physical. Okay, and then you got a pi power manufacturer, and then I've got a pi process. So the pi thermal, which is this value here, pi thermal is not just a number, but it's another formula. So it's a pi EL multiplied by the Arrhenius, and it takes into account the junction component temperature. Okay, and the junction component is the temperature ambient plus the junction to ambient thermal resistance multiplied by the power dissipated. Now that goes back to square one. We don't know the forward current. We know the voltage forward because if it's a silicon diode, 0.7, if it's germanium, 0.3. But we are stuck on this, and therefore we get to the end of the buffer basically, and we can't go any further. So we assume this is 1, say, so it's 1 watt, and that is basically multiplied by 100. Okay, and this pi L was the one that was really causing all the problem, because this is also is another formula behind. So it's not just a simple number, and that was the formula that was actually blocking us from inserting the setting of the diode, the 12 volt voltage and the 18 voltage setting, because it was by selecting a transient suppressing diode, it was basically erasing the possibility, it was giving this to 1 and removing the formula altogether, and therefore we couldn't set this value of the voltage. So anyway, to cut a long story short, we ran this into the Arrhenius model, and it gave us a whopping acceleration factor that we just couldn't believe it, 1501. So the question was, how does MIL-217 handle the diode? So we've seen how FIDES handles the diode. Let's have a look at how MIL-217 handles. Well, MIL-217 takes a very simplistic approach. The lambda part is the base failure rate multiplied by 5 pi, 3 of which are 1. Pi S is 1, pi construction is 1, pi environment is 1, pi Q actually improves things because it's 0.7, and pi T is 8, okay, it's 8, as we see down here, for a junction temperature of 100. So how can they be so different? And the clue was this number here, 3091, because when we looked at the FIDES formula, it didn't have any 3091, but it had 11,000, okay? So although it had the base failure rate, which was higher than the FIDES, but it was certainly much more softer, if you want, on a component, okay? So we ran this, we figured out the acceleration was 8, and therefore from there, we could get the activation energy. The activation energy was not 0.7 like it was in the FIDES, but 0.26, because obviously the Boltzmann constant doesn't change. So we wanted to look into that a little bit more, and so we went into one of the reference of MIL-217 that turned out to be quite an interesting document. The only downside, you couldn't download it, so you had to look at it on a screen, and that was really causing a lot of eye pain to making your eyes watering because it was not easy to read. But we picked up this document, which is a reliability prediction model for discrete semiconductor device dated 1988. And is a 344 pages, and we found on table 423 the activation energy data summary for all semiconductors. Okay, sorry, discrete semiconductors. And in this unreadable table, we found the transient suppressor had a proposed value of 0.33. So it was obviously very low value. We identify as 0.26, but it had a 0.33. And looking at here, this was the lower value of a test data that they obtained. We didn't go, it was quite difficult to read this document, so we didn't go into investigating even further and why would they use this number. So while it was raising a whole list of questions, we declined to go any further because otherwise this would have become a webinar on diodes. So, results. So these are our part of our BOM. On MIL-217, on Telcordia and FIDES, and let's look at the actual results. So we said it's about 250 components, and the MIL fit turns out to be 26,000. The Telcordia turned out to be 332, and the FIDES turns out to be 1,442 fit. Okay, so failure in billion hours. Obviously, we got a big unknown because we don't have the data, the real data. If we had the real data, that would have been obviously the most interesting. But that's why we did a comparison of components where we had components. So I don't want to draw any conclusion in terms of this is the norm or this is an indication of how much bigger it should be. It's quite clear that MIL-217 is, although it's very simple, as we've seen in terms of the actual calculation, but is well out of what the other two are in terms of prediction. And if we were to put these three together and see what chunks of each one takes, we could see that 93, almost 94% is taken by the MIL-217, 1.2 is taken by Telcordia, and 5.1 is taken from FIDES. So these come to the result, and we've gone a little bit over the top. In terms of conclusion, what we can say about the conclusion, we can say that, as I said before, we were particularly surprised how the Telcordia was close to the manufacturer data for the components we've analyzed, and that's why we decided to choose one of each type. And the amount of effort required was very, very little compared to other components. The FIDES, we were particularly impressed with the FIDES because it was not a matter of putting pies, but it was a matter of answering questionnaire. That was looking at almost like the design for reliability process, the actual design process, and that was extremely thorough, and we were particularly impressed. For a military application, I could see FIDES being particularly the top one. We didn't have much to say about the MIL. I mean, obviously they were pioneering those days, but obviously these days are now long gone. Okay, and that's it. Thank you for attending this webinar.